The objective of this example is to offer a means in evaluating the impact on concrete stresses when reinforcement is present. In the general case, when a concrete segment is provided with non-pre-stressed reinforcement, the applied actions at the ends of the segment will be resisted jointly by concrete and reinforcement. The participation of concrete and reinforcement in resisting applied loads depends on their stiffness at the time the load is applied. Initial forces will be redistributed between the concrete and steel due to creep. At any given time, the resultant of the stresses over a cross-section is in equilibrium with the applied actions on the section. The distribution of stress over the cross-section, however, depends on the load history and construction of the associated segment. ADAPT-ABI offers the capability to output the stress developed in both concrete and non-pre-stressed reinforcement, along with that portion of moment, shear, or axial load associated with each. Through use of the rebar command, these results can be output for any pre-capture stage. The structure for this example is a balanced cantilever bridge extending 55 feet to each side of a 60-inch by 60-inch by 35-foot tall pier. Each cantilever is composed of 8 segments with tapered cross-sections other than that at the pier top. The structure consists of 2 cases. The first case has a reinforcement ratio of 5%, and the second case has no non-pre-stressed reinforcement. The construction sequence consists of 5-day increments ranging from day 1 to day 45 and observation stages at days 50 and 100. At day 45, a 10 kip per foot line load is applied to the structure. At each installation stage, straight tendons are stressed and located above the centroidal axis so as to impose a constant positive moment to offset negative moment due to self-weight. This example will focus on the validation of results at the I node, top fiber of frame element 16, which is the first element to the right of the pier, and at the J node, top fiber of frame element 15, which is the first element to the left of the pier. This is where moment will be maximum for this particular example. The validation for 15 will take place with the 0% reinforcement ratio, and the validation for case 1, or element 16, will take place using a 5% reinforcement ratio. We now see a graphical representation of the structure to be validated, and specifically we're going to be validating in case number 1 the I end of frame element 16 at the top, and for case number 2 the J end of element 15 at the top. We also see an image which shows the notation and the orientation of tabulated stress output when the rebar command is used. So we have output for the node number 1 at the I end, node number 3 at the J end, and also node number 5 at the centroidal axis. Moving now into the graphical interface of ADAPT-ABI, we see the structure. We can review some of the input. We have a 10 kip load acting downward. This load will be installed on day 45. We can also review the tendons that we've input from top to bottom. If we open a tendon, we have 10 strands, 1/2 inch diameter strands. The stressing occurs on different days. The shape is a straight tendon. For example, this is 4 inches from the top, and the tendons sequentially just shift down 4 inches from each previous location. So we'll use the tendon data to validate case number 2. At the left side of the screen we see the project browser, which shows us the different stages and what occurs at each stage. We'll go ahead and review that. We're going to go to a developed view of the structure, and we'll review the step number 1. We can see that the pier and the support are built. Step 2, the pier top. Step 3, we continue to build out the segments of the cantilever, and so on. As we shift up to step number 10, we can see that the 10 kip per foot load is now applied to the structure, and then finally the last 2 steps are just observation days at 50 and also at day 100. Under the Material tab, we're going to go to Concrete. Under the concrete mechanical properties, we can see we have an ultimate creep value of 2. This is the ultimate creep coefficient in calculating the creep strain, and also the ultimate shrinkage value is the ultimate shrinkage strain that we use to calculate the different strains at each individual stage that are time dependent. Going back to the Material tab and the Mild Steel tab, we've set here the reinforcement ratio to 0.05, and we'll go ahead and apply that. and we're going to generate an input file for this particular structure. We want to now go back to process and we want to edit the input data. So we're going to scroll down to day number 45 in the sequence, and after the output we're going to select rebar and type that in after output with a space. We'll go ahead and save that. We're going back to the process bar and we're going to execute the model. We'll now move into the validation for case number 1, which occurs at frame element 16. Under Process View Results, we're going to take a look at day number 45 where the load has been applied, and the first thing we'll look at are the moments. And we can see that the moment at frame element 16, the I end, is negative 1.88 pound e to the positive 8 pound-inches. So this is the value that we're going to be validating first, and how we obtain that value, and then from there we're going to move into the stress calculation. So we can close that, and to open up the values and the different output we can go to Reports, Geometry and Analysis Results, and if we use the find function we can say find, and we're just going to say day, and if we continue to press enter we can scroll down to day number 45. And then we'll go down to section number 111, which is the frame element stress output, and this is the output that we want to review for both the moment and the stresses in the concrete alone. So we're going to scroll down to frame element number 16, which is here, and we'll review these results in more detail. In review of the input file, we can see that at day 45 there are several nodal loads acting on the structure. These were discretized from the line load of negative 10 kips per foot. We also have a solve and an output command with the token rebar, which will allow us to output the results for both concrete and rebar. In section block 111 we're going to focus on frame element number 16, and we're going to validate the stress when rebar is present with a uniform intensity of 0.05 or 5%. This is case number 1. We're going to validate the results at the I end top fiber. So to determine the concrete moment, we're going to take the total moment and subtract the rebar moment. This results in negative 1.81 e to the positive 8 pound-inches, which is what the results show in section block 111. We can also do the same for the axial force in the concrete. This results in a force of negative 8.143 e to the positive 5 pounds. In determining the sections, we use a typical stress equation where we're going to take the moment divided by the section modulus plus the force divided by the area. The frame element number 16 is represented by a 60-inch by 60-inch section, so we calculate S top as being 36,000 inches to the third. The area is 36,000 inches squared. And finally, our hand calculation by stress equals 4801.8 psi in tension, and ADAPT reports 4801.7 psi in tension. This is also shown in section 16 at node number 1, where stresses at points is reported. We can also see this in section 108, element 16, at the I top stress. Case 2 is the stress validation when no uniform rebar is present. This validation will occur at frame element 15, the J node at the top fiber. We've broken up the self-weight and the line load into discrete point loads acting along the span. These are shown on the slide. The balancing moment is also calculated by taking an assumption of 50% long-term loss at day 45. The effective stress per strand is 196 ksi, where the effective force per tendon is 300 kips. The resultant pre-stress moment at frame element 15 was calculated as 2450 kip feet, and the moment at frame element 15 is taken as negative 1.8876 e to the positive 8. This is essentially the same that's reported by ADAPT. We're now going to review the model and the changes made for case number 2. In ADAPT-ABI, we're going to go back to Material, Mild Steel, and set the reinforcement ratio to 0. This will suppress the contribution of steel in resisting sectional actions in developing stress at each frame element. From the process menu, we're going to generate an input file, and in review of that file we can now change and add the token rebar at day 45. After the output command, we'll type in rebar, we'll save the file, and now we're going to execute that. Once the model has been executed for the analysis, we can go back to Process, View Results. We're going to scroll down to day 45 in the day browser. And reviewing the moment at frame element 15, we can see that the moment at the J end of frame element 15 is negative 1.882, which is the same as our hand calculations from the previous slide. We'll exit Viewer and generate the report. We're going to scroll down to day 45 and go back to section block 111 to review the results at frame element 15. Continuation of case number 2, the stress validation when no uniform reinforcing is present. We'll review data block 111 for frame element 15 at the J end. For concrete, we can see that the bending moment equals that of the total moment, which is negative 1.88 e to the positive 8, with zero contribution from the steel. We can also see that the axial force in the concrete equals the total axial force of negative 1.96 e to the positive 6 in pounds. The stress is calculated at the top fiber of the J node for frame element 15. The stress calculation is similar to that for element 16, using the section modulus and the area, and also the moment and the force from the previous slide. The frame element is 60 inches by 60 inches, S top is 36,000 inches cubed, the area is 3,600 inches squared, and the resulting stress, calculated by hand, is 4562.7 psi in tension. ADAPT reports 4682.3 psi in tension. This results in a 2 to 3% difference. In section block 108 for frame element 15 at the J top, we can report this value from ADAPT. This concludes the video tutorial on stress validation when uniform reinforcing is present and when uniform reinforcing is set to 0.